We continue our discussion of analysis of variance now by recognizing that we may want to account for the degrees of freedom when we construct our R square. So recall that the total sum of squared errors, the total variation in our response variable was written this way. So it's the sum over all the data points I equals 1 to n of the squared difference from the observed value yi from its mean. And we can think of this as an estimator of sigma epsilon squared, which was the variance of the noise terms. And we can think of that by considering what would happen if we multiplied by 1 over n minus 1. That's the sample variance of the yi's, which we would call sy squared. Now let's think about the idea of coming up with an unbiased estimator for the information in the regression predicted by the regression, the variation in the regression predicted by the regression itself. In order to define that, we will need what we call the mean sum of squared errors, or the mean sum of squares, MS. And we're going to define that in the following way. So note that this here is what we had called the sum of squared errors, SSE. But now we want an unbiased estimate of what that is on average, hence the word mean. And to get that, we multiply by the degrees of freedom left in the system after estimation of the betas. Recall that estimating the betas consumed 1 plus p degrees of freedom. So this is what's left. So to get that average or mean sum of squared errors, we multiply by 1 over n minus p minus 1 over the degrees of freedom left in the system, in the same way that we do that for the sample variance to get the unbiased estimator. And so you can think of this as the average sum of squared errors when accounting for degrees of freedom to get an unbiased estimator. And also recall that this SSE was the variation in the regression that's unexplained by the regression itself. So this is the average in the unbiased sense of that. So the average variation in y that's not explained by the regression. And so this is what we're going to use to define our adjusted R square. So recall that our R squared could be written as 1 minus the sum of the square errors over the total sum of squares, which we can rewrite as 1 over n times the sum of squared errors divided by 1 over n times the total sum of squares. And this gives us a biased estimate in the numerator of the average sum of squared errors and a biased estimate in the denominator of the total sum of squared errors. So we adjust. To get the adjusted R squared, by instead of multiplying the top by 1 over n, we multiply it by 1 over n minus p minus 1. And in the bottom, instead of multiplying by 1 over n, with that sample variance intuition, we multiply by 1 over n minus 1. And we notice that in the numerator, we now have that mean square error. And in the bottom, we have what we call the total mean square error. And this gives us a new version of the R square that, again, adjusts for bias. And again, the reasoning is that the numerator is now the unbiased estimator of the average sum of the squared errors, And the denominator is an unbiased estimator of that sample variance of the y's. Now it's important to notice that typically the adjusted r-squared is close to the r-squared. We see with r-squared here we have 1 over n and 1 over n in top and bottom, changing to 1 over n minus p minus 1 in the top and 1 over n in the bottom. Usually doesn't change much because n is typically much larger than p. And so 1 over n minus p minus 1 is typically not that much different than 1 over n minus 1. But you will get a slight difference. And the idea is that you do this as an adjustment for bias. And so this gives us another way with the bias adjustment to measure the quality of our regression. And again, that adjusted r-squared is a biased adjustment for the percentage of the variation in the regression that is explained by the regression. So the percentage of the variation in the response variable that we can explain by the regression. And so we want to see a larger number. This will be something between 0 and 1. And the closer it is to 1, the better the explanatory power of our regression. And just speaking in general, whether we're talking about r-squared or adjusted r-squared, you also have to keep in mind the context in which you're working. If you're actually doing something with, say, physical science, so you're doing something in physics or engineering, an r-squared close to 1 is going to be something that you want. But if you're working in the social sciences, say in economics or in finance, then a lower r-squared, say 20%, is still considered to have some explanatory power that is quite helpful, because you're not going to get in many different settings the same type of high r-squared that you would if you were doing something that is actually tangible in the sense of the physical sciences. It's extremely important to recognize that when you're looking at your r-squared, you need to think about the context in which your regression actually is living. We'll look at more in future lectures ways of understanding and critiquing a regression, but really the r-square is a key tool in determining just how good your regression is actually doing at explaining the variation in your data.